All right, so we're talking through some good old thermodynamics. We're still going to be focusing on the first law of thermodynamics because that is the majority of what you'll have to worry about. And as long as you're able to understand the first law and its applications, you'll be able to do most of what you'll be touching on the first few weeks of the class. So, as a quick reminder, what is the first law of thermodynamics again? Anyone want to shout it out?
It's the change in energy is equal to the heat added minus the work done by the system.
Exactly. So the change in total energy, or delta U, make it a little smaller. So delta U is equal to the.
Felicity sharing your screen.
Oh yes, I am. You have a good point. There we go. I started recording it, and I forgot to start sharing it on Discord. But so yeah, we have delta U, which is the total change in energy of the system, is equal to Q, which is the total heat added to the system, minus the work being done by the system. So essentially, the total heat coming in minus the work going out is equal to the total change in energy. And that's really, as long as you're able to understand that, and as long as you're able to understand how the internal energy and the work relate to volume and pressure and temperature. So, like, what is the change in internal energy? How can we relate it to pressure, volume, and temperature?
We can relate it to temperature, which is part of the ideal gas law.
And what's the ideal gas law again?
PV is equal to nRT.
Yep. PV is equal to little n, which is the number of moles, RT. Or you might see it written as big N, which is the total number of molecules, times Boltzmann's constant, times T. The same thing, they're equivalent, where little n times R is equal to big N times KB. And so how do we relate delta U to the temperature?
We know that the internal temperature over the degrees of freedom is
Yep.
equal to 1 over 2 Boltzmann's constant times temperature.
Is equal to 1 over 2 times Boltzmann's constant times the temperature. Is that for a total system, or is that for an individual molecule, or?
That's for an individual molecule.
Yep, exactly.
Multiply it out with Avogadro's number.
What was that?
We'd have to factor in Avogadro's number.
Exactly.
Number of moles.
So, yeah, to get the total energy of the entire system, we'd have to multiply this by the total number of molecules, which is just big N. And since we said that, little n times R is the same thing as big N times KB, we could then also write this as half little n RT. That's for the total system, not just a single molecule. And what's our degrees of freedom for most examples you'll see in this class?
For monatomic gases, it would be 3. For diatomic gases, it would be 5.
Exactly. And so now, what is the work done by the system? How can we relate that to the quantities in our ideal gas law? Anyone else apart from Matthew? Let's at least get someone else in here, because I know Matthew's just going to run through all these. How do we relate the work to pressure, volume, temperature, etc.? You take a look at the equation sheet. It should be in here. It's going to be a little integral down here at the bottom, where our work being done by the system is the integral of P dV. So what does that mean? What does an integral essentially mean in terms of, like, if you have a PV diagram?
If you graphed it out, it'd be the area under the curve.
Exactly, yeah. So we have, if this is our PV diagram, and our function looks something like this. It'd be our total area under the curve. And we're obviously integrating from an initial volume, so like from right here to right there, to our final volume. That's literally all you need to know for Unit 3. Units 2 and 3 are, I think, Unit 3, and Unit 3 is thermodynamic process in the first law. I can't remember if that was also included in Unit 2. But that is literally all you need to understand what's going on. You know, first law of thermodynamics, PV equals nRT, and delta U is equal to half NKBT, and the work by is equal to the integral of PdV. So let's go ahead and hop in and do some examples, because that's honestly the best way to practice this, is work through some examples. So we're going to have 4 moles of a monatomic ideal gas is going to undergo a 4-step cycle. We're going to have an isothermal compression, an isochoric process where the temperature increases, and then an isothermal expansion, and then an isochoric process where the temperature decreases. So first thing, does anyone know what this cycle is called? It has a name. We have isothermal and isochoric processes. So for example, we have the Carnot cycle, and then we also have the other main cycle we're looking at that you guys have to know for this class.
It looks like the Otto cycle.
It's not the Otto cycle. Okay, what would the Otto cycle be?
Oh, does Otto cycle need adiabatic instead of isothermal?
I believe so. Let me actually double check that myself, because I'll be honest, I haven't taken a look at this since this time last semester when I was doing these. So the Otto cycle is, yeah, it's adiabatic and isochoric. But so isothermal and isochoric, does anyone know what this process is going to look like? Or what's it called? Starts with an S. Unless she's gone ahead and removed it from the curriculum without telling me. Yeah, fun fact, doesn't really matter. It's called the Stirling cycle. So our Stirling cycle is going to be isothermal and isochoric. So let's go ahead and I'll give you guys like 10 minutes to go through and draw what the cycle is going to look like on the PV diagram, labeling all our volumes and temperatures, and then label what direction the energy is flowing in each step. And so essentially do parts B through D. I'll give you like 10 minutes, then we'll go over it. If you have any questions, feel free to unmute or just type it in session text. All right, so we have our 4-step process. We have our isothermal, isochoric, isothermal, isochoric process. And first thing we want to do is we want to draw it on a PV diagram so we can sort of visualize what our process is going to look like. So we're going to have our pressure on the y-axis and our volume on the x-axis. So first thing is, what does an isochoric process look like on a PV diagram? First off, what does isochoric mean?
The volume doesn't change, so it's basically a straight line up or down on the
Exactly. Yep. So our isochoric processes are going to be some sort of a straight line up and down. And what do our isothermal processes look like? Is it going to be a straight line? Is it going to be like at a diagonal? Is it going to be straight horizontal? Is it going to be a curve of some kind? Isothermal process means constant temperature, right? And so how do we relate pressure and volume if our temperature is constant? Think about our ideal gas law. PV equals nRT. And so N, R, and T are all constant. So then P is equal to nRT over V. So it's essentially going to look like a sort of 1 over x curve. So our isothermal processes are going to sort of look like a 1 over x curve. So for our first step, we have an isothermal compression going from an initial volume to a second volume. So what is our isothermal compression going to look like? First of all, let me just draw an isothermal process. Let's say we'll draw it right here. So are we going from right to left or from left to right? So which one of these spots is V2 and which one is V1?
We're going right to left because it's a compression, so the volume is
Exactly.
constant.
Yep. So the first step, we're going from right to left. That means we're going from V1 to V2. And what's special about like this 1 over x curve that our isothermal process lays on? What's special about that curve? Or like, what's that curve called? Does the word isotherm ring any bells?
No matter where you go on that curve, the temperature will always be the same.
Exactly. So these curves are called isotherms, and essentially along the curve, the temperature is constant. So we'll call this T1. So then for our second step of the process, we have an isochoric process where the temperature increases from T1 to T2. So what is that going to look like?
It's going to be a vertical line.
Yep, vertical line, we going up or down?
Up.
Up, exactly. So we're going to have a vertical line straight upward because we're going to go from this isotherm along here to another isotherm higher up. And the higher up you go, the higher the temperature. So we got here. And then our third step is going to be an isothermal expansion from V2 back to V1. So what's that going to look like?
It's going to be another one of those rational curves just going to the right from the left.
Yep, exactly. So we're going to curve like this along another isotherm, and we'll call that T2. And we should end back at V1, so right there. And then for our last step, it's isochoric, where the temperature decreases back down to T1. It's essentially just going to look like this. Boom. So that's the 4 steps of our process. We have our isothermal compression, isothermal expansion, and there are 2 isochoric processes in between. And then we also have our labeled V1, V2, T1, and T2. So what direction is our energy going to be flowing for each step of the process? Let's start with step 1. How is the internal energy changing for this step?
It should be 0, right?
And why is that?
Because temperature is constant.
Exactly. So our delta U, I'm not going to label it on the graph. I'm going to make a little grid here. So our delta U for step 1 is 0. And what is our work being done by the gas? Is it positive or negative? is work going out or is work coming in?
Work is coming in because we're compressing the system.
Exactly. So our work by the system is negative, which means that the heat flow going into the system has to be what? So that our delta U is 0.
It has to be negative.
Yep, exactly. Our work being done by the system is negative, so work is coming in. That means in order for our total energy to be 0, our heat has to go out. So where heat in this case out is negative, where for work in is negative. I don't know why he uses this convention, but that's what he does. All right, now for step 2. Is our change in internal energy going to be positive, negative, or 0?
It's gonna be positive.
And does anyone else want to explain why that is?
Is it because it would be the same as Q?
And why? So yes, it is the same as Q, but why is it positive and not negative? How do we know that it's a positive change in internal energy rather than a negative one?
Because the pressure is going up, so the temperature is going up.
The temperature's going up, exactly. That's what we're trying to get at. So we're going up from T1 to T2 because our temperature is increasing. Delta U is equal to half NK, oh, by the way, this is delta T here, half NR delta T. So our delta U is, if temperature goes up, delta U has to go up. So delta U here is positive. And so then you said that that was equal to the work. And why is that? Oh, sorry, it's equal to the heat. And why is that?
Yeah, I was thinking that it was equal to the heat because work was 0.
Exactly. I couldn't have said it better myself. So work is 0 because there's no change in volume. That means our heat has to be positive so that there is a positive change in energy. So now for step 3. What's it going to look like? What's our delta U, what's our work, and what is our heat flow? It's going to be pretty similar to step 1, right? Welcome. We're going over part C here. Similar to step 1, what is our change in internal energy and why?
Our change in internal energy would be 0 because our temperature doesn't change.
Exactly. Once again, we're on an isotherm. It's an isothermal process. No change in temperature means no change in internal energy. And so is work being done by the system or on the system?
Work is being done by the system, so we'd have positive work.
Exactly. Positive work, which then that means we have to have positive heat. We have to have heat coming in so that work can go out. So heat flow is also positive. I should probably label these 1, 2, 3, 4. Now for step 4. What is our total change in internal energy? Is it going to be positive or negative?
Our change in internal energy will be negative.
Yep. And why is that? Anyone else?
The sum of the internal energy has to be 0
Because why?
because the positive and the negative has to be 0, like number 2 and number 4.
Mm-hmm. So why is number 2 positive and why is number 4 negative? Why isn't it the other way around? Like, pretend we don't know that for number 2 it's positive. So you're right. One has to be positive, one has to be negative. So why is it that number 2 is positive and number 2 is negative?
Decreasing
The what is decreasing?
the pressure.
The pressure, and that because the pressure is decreasing, what else is decreasing?
Temperature.
Exactly. The temperature is decreasing for step 4, which means the internal energy has to go down as delta U 1/2 NK delta T. Then the work being done by the system during step 4 is what?
0.
Yep, because no change in volume, which means that our heat flow has to be negative so that the total change in energy is negative. Boom. Does anyone have any questions about this? It's pretty simple if we just break it down step by step.
I kind of was curious about finding maybe the actual values, but just the equation for it.
I mean, that's basically leading into the next part. Was we're going to have some actual values and we're going to calculate stuff.
Oh, okay. Never mind then.
Yeah. But yeah, so I mean, as long we know what our volumes and our temperatures are, and from that we can calculate all of these using our first law and our ideal gas law, and delta U is 1/2 NK delta T. Does anyone have any other questions before we move into? We'll probably give you guys like 5 or 6 minutes to calculate them. All right, so let's take like let's say 5 minutes. So we'll go over at like 1:30, 1:36, 1:37ish. So we have given values. So V1 is going to be 10 liters. V2 is 5 liters. T1 is going to be 25 degrees Celsius, and T2 is 50 degrees Celsius. So I want you guys to calculate each of these. So delta U, the work by the system, and the heat flow for each of the 4 steps. It's usually take like more like 6 or 7 minutes. Once again, if you have any questions, feel free to ask. It'll take like 1 more minute, then we'll go over it.
Hey Dylan, do you have a brother named Aiden?
I do.
Oh, I actually know him. Cool, man.
Nice, yeah. Yeah, he's a sophomore. I think he purposely delayed taking physics for his science classes, so he's taking physics 121 right now, just so that I would graduate and I'd be gone by the time he took 122.
Oh, that's funny.
All right, but regardless, so let's go ahead and actually go over these. So we want to actually go ahead and calculate values for each of these. Let's start with step 1. Which is easier to calculate, the work done by the system or the heat flow? Which do we have a specific equation for that would be easier to do?
We have the equation for the work by that involves the natural log.
Exactly. And how would we actually derive that natural log? Is that actually given in the equation sheet? Oh, cool, it is. But so how would we actually derive this natural log?
You could express p as a function of v, and then just integrate it.
Exactly. And so what would that be? So we have our integral.
Our integral would be from initial volume to final volume.
Yep, so it'd be
We would
negative 5 to 10. I just put the negative sign out front, and it would be from 10 to 5, which is the same thing as negative 5 to 10.
And then we could just rewrite the ideal gas law, so it'd be small n RT over V.
Yep, so we have P dV, and P is equal to NRT over V dV, which then, you know, it ends up coming out to be a natural log, which is on your equation sheet. So we have is equal to nRT, throw a negative out there, and then our natural log of 10 over 5, so 2. And does anyone calculate a value? What's the actual value for this? We plug in everything. First of all, what would R be in this case? Do we have to do any unit conversions?
Temperature
Yes, so what would our temperature have to be?
has to be plus 273.
Yep.
To the coffee.
Exactly. Temperature 1 is equal to 25 Celsius, but we want to use Kelvin, so we add 273, so it's 298 Kelvin. So that's the one thing. But then also, is there anything else we need to know, like the volume? Are we able to use liters here and use our 8.314 ideal gas constant, or do we have to convert the units in some way? Is actually given.
I don't think the units are given, but if we wanted to figure out like the temperature, those kind of things, when we were like pressure, we would need to, because it's in liters instead of meters cubed.
Exactly, that's what I'm going for.
In the case of natural log, the unit would cancel, so the Q is unitless, so we wouldn't have to worry about it.
Exactly. So we just have to plug in our temperature in Kelvin. And does anyone calculate a value? We have 4 moles of our gas, by the way, in case anyone missed it.
I got 6,865.
6,865. Sounds like it would be about right. Let me. Yep, that's right. Well, 6,866 if you want to round up. But yeah, same thing. I'm actually going to just round it to 6,870. 6.87 kilojoules. And obviously negative. And our heat flow would be the same thing, right? So they're both going to be equal to one another. And so now, for step 2, we want to calculate our change in internal energy. And how would we calculate that? We have we're given the volumes and we're given the temperatures. So how do we calculate our change in internal energy? Anyone want to shout it out?
We can find the pressure.
What was that?
Yes. We can use the
You're cutting out. I can't hear you.
You can use the change of pressure times the volume.
Change in pressure times the volume, or just use the change in temperature, right?
Yes.
So we have our delta U is equal to delta U divided by the degrees of freedom. It's equal to half nR delta T. And what are our degrees of freedom in this case?
Three, because it's a monatomic gas.
Yep, exactly. 3/2 nR. Oh, okay. nR delta T. What is our change in temperature in this case? Yep, exactly. So delta T is 25. So we get a total change in internal energy of, let's say, 1.25 kilojoules. 1246.5 is the number I calculated. And then our heat flow has to be the same thing, right? Because our work is 0. Now for step 3, we want to calculate the work being done by the gas, and then that would also be equal to the heat flow. It's the same process as step 1, right? Where we just have a different temperature, and so we plug in our higher temperature, which would be 50 Celsius, which convert to Kelvin, that is 323, and then it's just the same exact thing, and then we now have a positive sign out front instead of a negative sign. So it's equal to nRT ln2, which plug everything in, calculate. Does anyone get a value?
I got 7,442.
Yep, exactly. So 7.44 kilojoules. Now for the last step, we once again just have we have our last isochoric process. So our work is 0, and how do we get the change in internal energy? Once again, same as step 2, through the change in temperature, 3/2 n r delta T, and that is going to be, it's the same change in temperature as step 2. It's just in the opposite direction, right? So that means it has to be the same change in energy, 1.25 kilojoules, just negative instead of positive. Does that make sense?
Yep.
What's N in the equation? N is the number of moles. So in this case, it would be 4 moles. Make sure you note that N is equal to 4 moles. Any other questions about this?
I was wondering if we were given pressure instead of temperature, could you, like, for instance, for that first step, like, you know how it says negative nRT ln2?
Yep.
Could you actually, like, use PV ln of the volumes?
So if you're given the pressure instead of the temperature, you absolutely, I mean, if you're given, for example, P1, P2, so it's a bit more complicated to do the isothermal process. What I'd recommend is still calculate a temperature. So use the pressure that you're given to calculate a temperature, and then just use nRT ln2. And how would you use the pressure and the volume to calculate the temperature?
PV equals nRT.
Yep, exactly. So PV equals nRT, and so say if you were given a pressure, you know, you're given your pressure of like 1 atm and volume of like 5 cubic meters, you would be able to calculate the temperature from that.
Got it.
Yep. Any other questions about this? All right. Oh, and I guess we missed part D here. So would the total net work be into or out of the gas? So is our process here going to be putting work out, or is it going to be pulling work in?
The work is primarily done by the gas, so work going out.
Yep, exactly. So we have our work is being done in step 1 and step 3. For step 1, work is coming in, and it's just this small area under the curve. And for step 3, work is going out, and it's this entire area up here plus the area under the curve. All right. So we have time for one more example. Since we spent a lot of time on this one, we'll sort of try to speed through this one a bit faster. Let me go ahead and save this as today's the 10th of February. We'll open a new document. I'll post these in the session documents channel. So in this case, we're going to have 6 moles of a diatomic. So diatomic, note that, ideal gas, is going to undergo a 4-step cycle. So first is going to be adiabatic expansion, and then isothermal expansion, adiabatic compression, and isothermal compression. So first of all, what is this cycle called? It has a special name. And this is one that confirmed you guys have seen.
The Carnot cycle.
Carnot? The fuck is Carnot? Butchering the pronunciation. It's Carnot. It's French. Yeah, it's the Carnot cycle. And if we want to draw it on a PV diagram, what would it look like? So first of all, what does an isothermal step look like? It's our 1 over x thing, right? So isothermal steps are going to look something like this. Now, what do adiabatic steps look like? What do adiabatic processes look like on a PV diagram? Is it going to be some sort of a straight line? Is it going to be diagonal? Or is it going to be a curve?
It's going to be a much steeper curve than the isothermal.
Exactly. So it's going to be a much steeper curve. So if we were to start at the same spot, the adiabatic process would fall much faster. So we have our PV diagram. So we have a Carnot cycle. And let's go ahead and take 5 minutes. Go ahead and draw the cycle on the PV diagram. And same thing as before, we want to know which direction, internal energy, heat, and work are traveling for each step of the process. So 1, 2, 3, 4, delta U, work, and heat flow. So we want to know if it's 0, positive, or negative for each step, and draw it on the PV diagram. I think like 5 minutes, so we'll go over it. All right, let's go ahead and go over this. So, first of all, what is our Carnot cycle going to look like on our PV diagram? So, the first step, we have our adiabatic expansion from V1 to V2. What is that going to look like?
It's going to be a steep curve going down from left to right.
Yep, exactly. So it's going to be some sort of steep curve. Let's say start here. Let's go a bit more like this. So a very steep curve going down from the left to the right. So this here is V1. Here's V2. And now our isothermal expansion from V2 to V3. What is that going to look like?
It's going to be one of the 1 over x curves.
Yep.
Going again from the left to the right.
So it's going to be it's not as steep, so it's going to be something like this. This is supposed to look like a curve, trust me. It's a less steep curve. Let me actually go ahead and redraw it. So we're going to have our initial very steep curve. Then we have our less steep curve. So V1, V2, V3. And then our third step is going to be adiabatic compression. So what is that going to look like?
It's going to be a steep curve going up, so from the right to left.
Yep, so it's going to look something like this. And then our last step is our isothermal compression, where we're going to go back to V1, and this is going to look something like that. So this is what our Carnot cycle is going to look like. So, what direction is our energy flow going to be for each of these 4 steps? So first of all, for step 1, what does adiabatic mean? Yep, exactly. So for steps 1 and step 3, we know that our Q is going to be 0. And once again, from before, we have isothermal processes. Anyone apart from Matthew, what does isothermal mean in terms of our delta U, our work, and our Q?
They should be equal because the amount of energy that leaves the system should be the amount of energy that comes into it in the different forms in order to equal out to 0 net
So what is
energy.
exactly? Yeah. So delta U is going to be 0 for each of them because no change in temperature. And so whatever we get for work and heat, we know it has to be the same. And then also for steps 1 and 3, because our Q is 0, that means our internal energy change has to be equal to the work done by the system, or the magnitude, and then they would be opposite in sign. So for step 1 is our work being done by the system, or a change in internal energy. So what is our change in internal energy? Is it positive or negative?
A negative,
And why is that?
because the temperature is decreasing.
Yep, exactly. Temperature is decreasing, negative, and that means that, obviously our work has to be opposite in sign from our change in internal energy. Another way you could see it is, we have a positive area underneath the curve. Now for step 2, is our work and our heat flow, are they going to be positive or negative?
Let's do it again.
Yep, positive. And why is that?
Because the volume is increasing,
Yep, exactly.
work done is equal to Q.
Exactly. Volume increasing, work being done by the system is positive. Now, step 3, our adiabatic compression. Our change in internal energy is going to be positive or negative? Positive, yep. Because for 1, we have to be opposite of step 1. And also, we can see that the temperature is increasing. We're going from one isotherm down here to a higher isotherm up here. And that means the work done by the system has to be negative. And in step 4, our work done by the gas and our heat flow both have to be negative because
Volume is decreasing.
yep, volume's decreasing. So is the total net work for this process going in or out of the gas? So is the gas doing work, or is work being done on the gas in total?
I think since the work is negative, like the negative values of work would be larger than the positive values of work. You'll have a negative work. So it's a net work into the gas?
Easy clap. There we go.
Okay.
Yes. So as you said, the negative work values, especially for this step up here, compared to, so for step 4, especially versus step 2, is much larger in magnitude, which means that in total our negative work is larger than our positive work, which means work is going in. So work in. And lastly, we're going to have actual values here. So we have V1 is 10 liters, and V3 is 20 liters. And then we have T1 is going to be 30 degrees Celsius, and T2 is 24 degrees. So we have 24 degrees Celsius, and then we have 30 degrees Celsius. And then we have V1 is 10, and then V3 is going to be 20 liters. Let's go ahead and calculate V2 and V4, and also calculate the internal energy, the heat, and the work for each of the 4 steps. I'll give you guys like just 1 or 2 minutes to sort of think about how we would do it, and then we'll just go through it together since we're starting to run low on time. We only got about 10 minutes left. To sort of start to think about what we're going to need in order to calculate these. All right. So, what are we going to want to? What are we going to need to use in order to? Let's first calculate V2 and V4. So, does anyone have an idea of what we could do to actually calculate these other 2 volumes? So we have our initial volume V1, and then we have V3, the largest volume. How would we calculate V2 and V4? First of all, let's start with V2. What would it be easier to calculate what V2 would be by comparing it to V1 or by comparing it to V3? I would say it's easier to relate V2 to V3. And why is that? What's special about step 2 here? What kind of process is it?
It's an isothermal, so we know the temperature is constant.
Temperature's constant, exactly. So how can we relate our pressure and our volume and our temperature? For example, using the ideal... Go ahead.
No, I was just going to say use the ideal gas law.
Yep, ideal gas law. So we have PV is equal to nRT. And we know that so our temperature here is going to be constant, and we should be able to, calculate first of all, I would say that the easiest way to do it is we have a constant temperature, and we have our initial volume here, V3, and we'll say we here have V3, and if we go up here, do we have a way to get the pressure, which then we would be able to use to calculate the volume, or do we maybe want to calculate the change in internal energy or the work being done by the gas here first? I think I'm overcomplicating this. I apologize. The way I'm thinking about it now, the wording is a bit weird.
Maybe, I guess the way that I tried doing it was, since we know that 2 of the processes, the internal energy is 0, the internal energy for 1 and 3 would be, we would use 3 halves nRT.
Mm-hmm.
And then for processes 2 and 4, we would perhaps use work equals nRT ln VF over VI.
I think it's the other way around, where 1 and 3 are... Oh, wait. Yeah. So, I think you... Hold up. We look at the equation sheet. We have our work... Oh, yeah, you're right. So, if we wanted to be able to calculate our work being done, let's go ahead. Let's not worry about calculating V2 and V4 for now. Let's start calculating what we can here in terms of the change in internal energy and the work being done by the gas and the heat flow. So for step 1, do we know what the change in internal energy is going to be?
I think actually maybe we're supposed to use 5/2 nRT.
You are absolutely right, and why is that? And I forgot about that, but
This is diatomic.
diatomic, exactly. We almost missed that. But so for step 1, our delta U is going to be, we know our change in temperature, right? It's going to be -6 degrees Celsius. So what is our delta U going to be? We said it was 5/2, right?
Mm-hmm.
And our delta T, which if we plug everything in and calculate, anyone get a value real quick?
I did my math right. 623.
623, let me see, times 6. I didn't get quite that.
Let me check. I probably plugged it in wrong.
Did you use 3/2?
No, I used 5/2.
Did you use, we have 6 moles of our gas here instead of 4.
Yeah, I used 6.
Okay. That's
So
weird.
I'll just read some numbers.
Did
Yeah.
you get 748?
Yep, 748.
Yeah, point.
Yeah, that's what I got. 747.9. But 748 joules.
I see. I put in 5 for the change in temperature.
Ah. Okay, that would make sense. I was just thinking like that. It's weird. Like it's a small percentage of the change. So it's like I wonder what you plugged in wrong. But anyway, so we have our change in internal energy, and so then we would be able to calculate the work done by the gas, right? And that's just opposite of that, right? Because our heat flow is 0. So work is equal to. Oh, we also have to note that it's a negative sign here for the change in internal energy. So we have positive 748. For step 2, our delta U 0. And then we can calculate our work by the gas, and it's also going to be the same thing as Q. And what would that be? How would we calculate it? Go to the equation sheet, isothermal. We want to use our natural log. So we have our nRT ln of V final over V initial. But we don't have our initial, right? We don't have our initial volume because we don't know what V2 is. So we're going to have to come back to this. Step 3, it's very similar to step 1, where it's just 5/2 and our delta T. And our delta T is the same thing, just opposite. So delta U is going to be positive 748 joules, and then our work is equal to negative 748 joules. Right, makes sense. So then for step 4, we have our work done by the gas. It's going to be equal to Q, and we have this nRT ln of V final over V initial again. And we don't know what our initial volumes for each of these 2 steps are. So there's another way we can relate the volumes and the pressures and whatnot to the in terms of an adiabatic process. Does he give it on the equation sheet? He does indeed. So has anyone seen this PV to the gamma constant before? Has it? I know he doesn't cover it too much in the class, but does anyone know how to use it? How we would be able to use it to calculate our whatchamacallit, our V2 and V4? So if we have P times V to the gamma, does anyone know what gamma is in this case? It's Cp over Cv. What would that be for a diatomic gas?
Would it be 5/3?
That would be for a monatomic gas.
Sorry. 7/5.
Yeah, exactly. 7/5. So our total, our P times V to the 7/5 is going to be equal to a constant, and that's what our line is here. And we can go ahead and rewrite this as P times V to the 2/5. Right? You know, I'm just now realizing that this is a lot more annoying than I originally thought. Why did I use this problem again? I think I remember having this problem last semester where I used this problem. But essentially, what we would want to be able to do is we have our P times V to the 2/5, right? How can we relate P times V? What is P times V equal to in terms of something we do know?
It's equal to small
P.
r.
What was that? You guys both talked at once. I couldn't really hear.
We can relate it via the ideal gas law to
Yep.
small n RT.
Yep, nRT times V to the 2/5. And we know that has to be a constant, right? So if we take it in our initial spot, we'll call it spot 1. So we have nRT T1 times V1 to the 2/5 has to be equal to nRT2 times V2 to the 2/5. And if we go ahead and plug everything in, obviously nr cancels out. So we want to calculate V2 in terms of V1. So V2 is equal to, so V2 to the 2/5 is equal to T1 over T2 times V1 to the 2/5, which then, if we go ahead and get rid of our 2/5 here by essentially multiply by a 5/2. How would we do this in this case? What would it be? All right, let's just leave it as this. V2 to the 2/5 is equal to T1 over T2 times V1 to the 2/5. Does that make sense? It's a bit more complicated and annoying than anything you guys will see. But basically, we could use that along with, and then we could do the same thing for calculating V4 and plug them in to get our values. Anyone have any quick questions? We're actually over on time right now. If you guys have any questions about this, I can answer them later. Feel free to just ping me in the server. But I've actually got to run. I have a COVID test in 15 minutes because I'm feeling a bit under the weather. But thanks guys for coming. You had one quick question, Armor?
No, I was just gonna say thank you, and I hope your test comes out negative.
Yeah, I'm pretty sure it's going to be negative. It just feels like a normal cold, but I just have to make sure because my girlfriend's parents are a bit older. They're in their 60s.
Makes sense. All right.
Yeah.
I'll
All right.
leave you to it.
Thanks guys for
Have a
coming.
nice day.
And if you
Thanks, man.
and if you didn't sign in, Google form and session text, but I'm pretty sure most of you guys did. All right, thanks guys for coming. See you around. Same time tomorrow.